Okay, so what we're doing is to have a quick review of the server discussed yesterday. And what we're looking at is a finite state machine representation of the operation of the server. So in state one, all that the server is doing is to wait until it gets a request. So whilst not a request, you loop back into that state one. When you do get a request, well, there's no action that's relevant to take, but you're going to change to state 2. And in state 2, well, you're going to move to state 3 almost straight away. But the two things that this state machine is going to do is, first of all, is to send a line to the client, providing that the file's not yet empty. There's more to send. And also you print the message, I've sent a line to the client. And in state 3, all that's happening is that you're waiting until you receive an acknowledgement from the client. And when you do receive an acknowledgement, you're changing back to state 2 and you're repeating the whole process again. But the action you take in moving from state 3 to state 2 is to print out a message received an acknowledgement. And remember, what we're trying to do is to implement an element of reliability in the form of a stop and go. You stop and go. You stop sending data until you receive an acknowledgement, and then you continue. If you're in state 2 and you discover that the file is empty, you've finished. So you change state perhaps into this fourth state, where you're just printing out the message that you finished or something along those lines. So all that remains to be done now is to have a look at the client, and this is a bit more, it's a bit simpler. So the client in merely finite state machine format is that you're going to write on each state transition line the input or event that takes place causing the client to change state, followed by, with a forward slash, the action or output. So I should really have said this, mention this in the case of the server. So in state 1, all that's happening is that you're sending a request. That's the action that you're doing. You automatically change from state 1 to state 2, and you on the way you're actually sending out a request. And in state 2, you're simply waiting for the line to be received. So whilst, let me add that, whilst the line's not received, this is stay in state 2. And when the line is received, when you've got a line from the server, the first thing that you do is to send an acknowledgement. And you can, if you want to, it's an optional thing, send out the message to the user of the client, but the fact that you've sent an acknowledgement, and also you could print out the line that's just been received. And you change state from 2 to 3. And when you're in state 3, in state 3, you can simply go back to state 2 and wait for the next line. And there's a sort of little observation. If you're in state 2, but you don't get a line for a certain period of time, it might be reasonable to assume that there's no more lines to receive. In other words, the server's done its job and it's sent the whole file. In which case you can simply finish, and you can measure the time waited by using a UDP method called SO timeout. You're waiting for a fixed period of time to give the client time, to give the server time enough to send the next line on receipt of the acknowledgement that you've just sent. So I think I've almost said everything I wanted to say. So I'll close this short video clip down. It's only a few minutes long, I know, but it suffices to give you an idea of what the finite state machine descriptions or representations of the two systems look like. You might find it easier to think about doing things in the more machine format. In other words, you can actually annotate the state transition lines, for example, between 2 and 3, simply with the cause of the state transition, and you can write the actions inside the state circles here and here if you want to. So I'll